from the College of Innovation and Technology, Florida Polytechnic University, Lakeland, Florida in the USA. I teach physics, basically physics 1 and physics 2, but I also carry out research on renewable energy, hydrogen energy storage, nanotechnology, material science, multifunctional materials, and many other fields. I would like to first thank Dr. Krishna Vedula for organizing this virtual academy meeting on this auspicious banner of Indo-US collaboration for engineering education. Thanks to Sridhar Nori for technical assistance. So today I'll be introducing, of course, it may take a couple of more volumes of lectures on this subject, but today I'm going to kickstart with hydrogen energy storage challenges for onboard fuel cell vehicles. There are too many jargons in here. Hydrogen energy, what is that? And why do we need to store that? And what are the challenges we face? And then why do we need to store and why do we need to use this hydrogen for what purpose? The fuel cells. So from this title, if you look at it, is hydrogen is very familiar to all of us because from the elementary standard and middle school, we used to come up with this letter called H or H2. That's so-called hydrogen, but we don't know the significance. At that time, we were not that much aware about what was the significance of hydrogen, because we drink water, we do all kind of water businesses, we use hydrocarbons, but every form of compounds, the water, hydrocarbons, or any other, even in animals, you do see some sort of hydrogen combination will be occurring in there. So the hydrogen is 1s electron, it's only one electron, which is spinning on the orbit of the orbital electron. But again, hydrogen is itself, it's an inflammable gas. So hydrogen can be useful for burning or any sort of, because it has a very high calorimetric value of compared to gasoline. So the hydrogen, one other advantage of hydrogen is it can easily combine with any metals or metalloids in a periodic table to become metal hydride. It will easily combine, like you can name it whatever the compound, like a CH, NH, pH. So you have a potassium hydride, so it can easily form a compound like a hydride with any of the elements on the periodic table. That's a good advantage for the hydrogen. So today we are going to store the hydrogen because the problem is it has a very good inflammable capacity. How we can store this hydrogen and use it as an alternative fuel? That's the topic of today. So let's go into the virtual academy. So this slide, the second slide, which shows about everything is in green. What that means, so far what we burn, like coal, oil, and natural gas, everything contains some carbon footprints. Carbon footprints could be direct hydrocarbons or carbon chains. So that causes a lot of calamities, like now you have seen that Nepal has got worstly affected earthquake, and also many other places, many calamities like tsunami was the worst one. So all these natural occurrences, natural catastrophes occurs. What would be the causes? Because these all, again, it's all natural things, but also it catalyzes by the man-made carbon footprints onto the atmosphere. So, are there ways to control the greenhouse gas emissions without harming the environment? What are the energy technologies that emit no or minimal CO2? So the only option for us right now to look into and do research into are renewable energies and alternative energy sources. Renewable energy, all of a sudden you get into more like idea like sunlight. Sun is very much available. So sunlight is the one that's called solar radiation. So solar, wind, and many other sources. So this slide represents various renewable energy sources which carries no or minimal CO2. First, let's look at the solar. The sunlight is very enormous. Unlike other sources, solar is almost limitless. Several parts of the earth receive good solar radiation, including India. Our sunshine state in Florida, we used to get about 600 to 800 watts per square meter. An hour of solar radiation on Earth provides 14 terawatt of years of energy. So it's very enormous. Solar energy is non-polluting and is available on all countries. There are two routes for solar energy generation. It could be solar thermal. That means you can take your heat and then produce the energy from that solar thermal energy storage or energy, or solar photovoltaics. The photovoltaics is the one what you see on your rooftop panels, the silicon, amorphous silicon or cadmium telluride solar panels like PVs. In solar thermal approach, the sun's radiation is converted to heat and is either directly used for water heaters. Directly you can convert the heat into electricity to get your water heater. And also we are talking all the time, when we talk about renewable energy, we also have to talk about sustainability. Because any technology which is not sustainable, then probably that's not going to come for long run. So the sustainability and clean energy should be focused if we are going to talk about green energy or clean energy. So the solar is very highly compelling. Why? Because it has a greenhouse mitigation, and also it is sustainable. The wind energy, on the other hand, in contrast to solar, wind power is a mature technology contributing about 73 gigawatts of capacity in 2006. The global wind energy generation at location with wind speed in excess of 6.9 meters per second at 80 meters above the ground is estimated to be 72 terawatt. It's much higher power, 72 terawatt of in years. However, it depends on the wind speed, wind direction, location, and so forth. So on this slide, I want you to point out on your left-hand side of your monitor, you will see the number of energy production facilities or resources such as wind, solar, nuclear, waste, coal, geothermal, and ocean thermal. On the right-hand side, if you look at it, there are a lot of utilization in terms of transportation, industrial, commercial, residential, and many other sectors. So how you are going to supply an energy which is produced from the production side to the end user side by means of transportation or by means of passing through the grids or batteries. So you have to come up with a technology which could be potential for transporting the energy produced from the production side to the end user side. Right. So on this, we are having this talk today to see that if I produce a hydrogen, as I said, that the hydrogen is in all the compounds and all the inanimate and animate things. So the hydrogen, primarily, let's take hydrogen can be harnessed from water. H2O contains H2 and O. So hydrogen can be derived from water, and then you want to use the hydrogen to use for your transportation. Then it has to either store it in a battery or a smart grids or into a transportation vehicle. So transportation vehicle at a high pressure, it's kind of risky because you have heard about the many accidents because of the hydrogen gas explosions. You don't want to go with the hydrogen at a very high pressure gas, about 10,000 psi or 20,000 psi. So we are going to talk about today that what are the mechanism of storing the hydrogen so that I can safely take the hydride canister from one place to another so that I can use it for my either genset or any other applications. So the next slide is primarily about the hydrogen. So this is called hydrogen fuel cell technology. Again, the application is a fuel cell. Back in India, we use mostly internal combustion engines, IC engines, for using our gasoline vehicle or diesel vehicle. But the problem is, again, the conversion efficiency. If you just take your internal combustion efficiency, it could be about 30 to 40% of efficiency compared to 65% and above for fuel cells. The fuel cell is made of two electrodes, cathode and anode, and then separated by a membrane called proton exchange membrane. What that means, it takes the hydrogen and permeate the hydrogen through the electrode, whereas the electron produced will pass through the electrical lines, and then the hydrogen pass through the electrode will combine with the oxygen to form a water, moisture. So basically the hydrogen combined to oxygen to give power. At the same time, you get your carbon-free exhaust, right? Okay. So in this slide, it is about what do you call it? Resource generation. Resource generation. What that means? You are producing a hydrogen from electrolysis of water by using a sunlight and then the PV electrolysis. Once you produce a hydrogen, then it has to store in an intermediate storage. The storage could be the gaseous cylinder or batteries or any storage materials. Once you store this, you want to use this hydrogen back into your fuel cell or internal combustion engine. That is the black one which showed. So you can use it, consume the hydrogen in here, and the exhaust of the fuel cell or the IC engine will produce water. It burns back to water. So the bottom line is the hydrogen produced from one place, stored at one side and used at another side, and then finally eventually it has to go back to its water again. So water is resource generating, and also if you look at the heat of combustion of hydrogen is about 33.3 kilowatt hour per kilogram. And of course, we will replace the IC engine with a fuel cell stack so that you can produce chemical fuel conversion like a hydrogen oxygen conversion and back into produce the energy, electricity. So the three things which are important here, one is hydrogen is very abundant in the form, it's not in the element form, but it is available as a compound form in the universe, and then it can be produced from hydrogen from oxygen by applying electrical signals. That is called electrolysis, and then you can store it near zero greenhouse gas emitter. So the exhaust which is coming out of this vehicle, which is zero polluted vehicle, that serves the purpose for our fragile planet Earth. Those who are electrical engineers, they might like to see this kind of circuit diagram. So this shows that on one end, it's a very similar concept what I discussed in the previous slide, but it is put into the perspective of what the network is about. So on one end, you have a sunlight which uses for photoelectrolysis, solar cells and solar collectors that use for either heat engines or directly used for electrolytic cell. So on your left hand side, all these sources are listed as renewable energy sources like wind, potential energy and kinetic energy. Now even people are talking about human energy. So you are spending energy for doing things, okay, and the same energy you can tap it and then use it for running your mobile or some sort of automotive. That would be like whatever the excess energy which you are spending from your human body, that could be turned as an energy, then you can use it for any applications. So that's called potential and kinetic energy. Oceanic thermal, that means you can see the level of the ocean where the top layer and the bottom layer, there is always temperature gradient about half a degree to 1 degree or more than that. Then you can tap that delta T so that you can produce your electricity or electrical turbines to work on that. And then there are a number of energies like fossil fuel, so-called, is a coal, gas and oil. Geothermal is a one which is in specific places. Geothermal works good. And there are a number of energy which is called fission and fusion. Those who are in physics, they might read about the fission reaction, that's a nuclear reaction. The chain reaction which causes the enormous energy, that's E is equal to mc square. So if you have fast moving neutrons bombarding with heavy nuclei that produce number of fissile particles, at the same time it produces energy, that's called the nuclear energy. Then nuclear fusion, which occurs in sun, probably you can also simulate inside the reactor, that's a laser reactor. Again, on the left hand side, all these are producing hydrogen or producing the sources. And then on the right hand side, you can use it for many applications like domestic transportation, synthetic, industrial and power stations. What is lacking behind in between is the storage. The hydrogen needs to be produced because it's a very volatile, and also it is very easy to escape upper atmosphere. So you need to pack this hydrogen either in a high pressure cylinders or liquid type of liquid, making it into a liquid nitrogen, or in form of a metal solid state hydrides. We'll come to that. So I'm going to throw about two scenarios. One is the storage, the production of hydrogen without any storage and with storage. So the first part of the slide, which shows that the hydrogen which is produced by electrochemical treatment, where you can produce the hydrogen that can either you can use it directly into internal combustion engine or the fuel cell. That means use on demand. That means use on demand in the sense like you can only produce a hydrogen as long as the vehicle is using, and then if the water is depleted or the fuel is depleted, then you have to go back and fill up the water and so on and so forth. So that's not the safest and also inexpensive way. It's an expensive way of storing without storage. You are using hydrogen on demand. A number of companies like Millennium Cell and many other companies, they float this sodium borohydride for treatment of plants and also using for the onboard storage. But the Department of Energy, they put a full stop onto that because they are not viable. Because you know the sodium borohydride, it produces hydrolysis to produce enormous hydrogen. At the end of the day, you produce some sodium borate that needs to be rejuvenate or recharge or renewable. So that is a kind of a tricky there. So we need to look for something reversible hydrogen storage. So the first option has some limitations. The second option, where you have the storage site and also the PV panel to produce, and also there is the useful application like fuel cells and ICE engines. In between, there are a number of storage methods where you can store the available hydrogen and then use it on onto the onboard fuel cells. That means you can take the hydride canister and fit it on your IC engine or fuel cell. Therefore, you can go up to 300 miles of range, about 75 to 80 kilometers of range for one charge. So that we will come. And there are some method called reformer. They also use for reformer to refine the hydrogen and store it in a metal hydrides if it is hydrocarbon. Right. This is an animation of how does a fuel cell work. So initially the hydrogen comes from a tank or any hydrogen storage material. That hydrogen is allowed to permeate onto that's a plus, hydrogen plus, permeate onto the proton exchange membrane and then mixed with the available oxygen from the atmosphere, it forms a water. On the other side, the hydrogen produces also electrons. The electrons pass through the electrical lines of a circuit that produce electricity. So the hydrogen is used as a source. At the same time, it produces into water, so you don't have to worry about the carbon species. Whereas the electron is enough for lighting, or probably you can use your utilities like fan, light, and other utilities to function. So for this, what do we need? We can supply the hydrogen from the source. We can use these fuel cells to run for producing electricity, but something to need to store the hydrogen. The storing hydrogen should go before the fuel cell. That way the hydrogen, the hydrogen can be constantly flow into the fuel cell. Then that can go into your for producing your automotive power. So those all 5-day diagram shows that how the PEM cells works in this case. Right. So now let me come into little close to what I'm going to discuss about. So on the one side, the forecasted production of hydrogen needs is about 150 million tons per year. This is of the report by Dr. Dresselhaus from MIT. She did this for a special volume for hydrogen in 2005. So number of methods have been used, but still the targeted 150 million tons is not achieved so far. Probably now it could be around another 10 or 15 million tons per year. And on the fuel cell side, the cost is a big factor. The cost of fuel cell stack. So the Department of Energy goal is to bring equivalent to internal combustion engine about $30 per kilowatt, whereas the forecasted price is about $3,000 per kilowatt. Again, these numbers may be little changing because it's about 10 years now. The storage is the one which is in between the production and the fuel cell. The storage is supposed to be 9.72 megajoules per liter of hydrogen. So far, we have achieved up to 4.5 to 5 megajoules per liter of hydrogen compared to gaseous hydrogen, which is 10,000 psi. So there are a lot of drawbacks and a lot of challenging issues. How we can we will be achieving the targets set forth by the Department of Energy or the automakers. So the gaseous hydrogen, which I'm interested for today, and probably it will continue in future discussion for particular topics, is about gaseous or hydrogen storage. So I take the hydrogen on one end and then store it in a canister, and then finally use it for my fuel cells or stationary or automotive applications. Before coming to this background, I would like to touch upon my background where I started my hydrogen storage research. I was working for my problem related to hydrogen at Banaras Hindu University in the Department of Physics, BHU. So where I was exposed to this technology by my professor, advisor, Professor O.N. Srivastava. So he was developing at that time some of the novel metal hydrides for storing into motorcycle, so that it can take about 70 to 80 kilometers of a range, and then you can refill it with hydrides. The reason is the hydrides or so-called hydrides are reversible. That means you can store and release the hydrogen back and forth, and therefore the hydride becomes spongy. So it becomes more like fluffy, so that it can absorb more hydrogen and desorb more hydrogen. So I did my PhD there in BHU, and then I went for a postdoc at University of Hawaii and the University of South Florida. So still BHU has a number of vehicles transform into hydrogen fuel cells or hydrogen with the internal combustion engines for running on the roads. So with this introduction, I would like you to take an attention for a comparative chart of the volumes. I wanted to fill in about 4 kilograms of hydrogen in different systems. If I go with a 4 kilograms of hydrogen, if I want to fill it in a high pressure compressed tank, which is sitting like what the label is called H2 200 bar. So if you take a 400 kilograms of hydrogen, if you want to fill it in a tank, you need this much volume, that is H2 200. If you look at the label, that much volume is necessary for using a gaseous hydrogen. For the liquid hydrogen, liquid means you are cooling the hydrogen into first liquid nitrogen. Liquid nitrogen is about 77 Kelvin, and then cool down to liquid hydrogen, that's about 21 Kelvin. So you are just freezing and cooling that hydrogen and pack it in a canister. That only probably can be done by space shuttle vehicles like ISRO or NASA or many other agencies, they can spend much billions of dollars or billions of rupees to use this liquid hydrogen for space shuttles. So the volume is comparatively less, but it's not enough so that you need to go further down. So what we did in the back in our research, that we used some metal hydrides made of periodic table elements like lanthanum nickel aluminum or lanthanum nickel mesh metal. Lanthanum is a rare earth material. Nickel is transition metal compound, and then aluminum, and then we make a compound so that this compound or magnesium nickel aluminum, magnesium nickel iron, etc. So these compounds, they have this full power of absorbing the hydrogen at operating conditions, like it could be a room temperature, it could be a mild temperature, it could be a little high, like magnesium hydride. It takes about 320 degrees Celsius. But you can store the hydrogen in a form of atoms. Like you can package the hydrogen in terms of atoms, not in molecules in case of gaseous hydrogen or liquid hydrogen. So you can store it as a packing the atoms, the hydrogen atoms in a lattice. Therefore, you get more number of area to cover this, so that you need the volume required for storing this hydrogen. The same 4 kilogram of hydrogen in a metal hydride is much lesser compared to the gaseous or liquid hydrogen. On your right hand side, you will see that the button, the metal hydrides, which are made of aminoboranes, aminex or aminoboranes. These aminoboranes, they store hydrogen reversibly and then use it for your fuel cells or any internal combustion engine. For a comparative study, the solid hydrogen storage is given, and also the canister hydrogen storage in terms of this is a company called Ovanix. Ovanix in Ovanix in Michigan, they developed this hydrogen canister for reversible hydrogen storage, and also use it for stationary and charging purposes. And then we have a motorcycle, and now it is many of the companies like Ford and Toyota, they come up with the hybrid Prius car, and Prius is more like nickel metal hydride batteries in there, and also we have some Nissan Leaf. So these are all cars which now coming up with fuel optimization and many other things. So the challenges towards us is, how can you store the hydrogen in gravimetrically, the system gravimetric capacity? That means how much by weight you can store the hydrogen, and also how much volume you can store a hydrogen for what? For about 300 miles of range of vehicle operation, and storage system cost, durability, and environmental health and safety. So for the system gravimetric, so far 2015 targets is about 0.3 kilowatt hour per kilogram. So this is on system level. It is about 3% or 3 to 5% storage capacity. Volumetric capacity also is given in terms of system level. Of course, there are two types of storage capacity available. You can calculate. One is materials capacity and one is system capacity. So this listed item is based on the Department of Energy system targets. So we have, and also the storage system cost should be $2 per watt or $2 per kilogram hydrogen. So these are the DOE targets which we are working on to get our research done. This one is about hydrogen storage. So now we are getting to the subject, hydrogen storage methods. What are the methods available on Earth so that we can store the hydrogen? The first one is high pressure hydrogen. The high pressure hydrogen means you can take the hydrogen and store it in a gas bottle or a high pressure tank. So the high pressure tank is about 800 bars of hydrogen. It's a very high pressure. The gravimetric density is about 13 and volumetric is 40, less than 40 kilogram hydrogen per cubic meter. And temperature, you can store it at room temperature. The problem with this is compressed gas in lightweight composite cylinders. So you need to develop specialized cylinders to store this hydrogen, like Kevlar composites and other stuff. Liquid hydrogen, it is a size dependent, but it stores about 70.8 kilogram hydrogen per cubic meter by liquid, stored at 21 Kelvin, that's a liquid hydrogen temperature, stored at 1 atmosphere. So the problem with this is it's very expensive. Also, a lot of cryogenics involved. So one other thing is liquid hydrogen, if you leave it for almost 1 day, you will see no more liquid nitrogen there in the container. Why? Because of the orthopara loss or conversion. The third one is adsorb the hydrogen. That's called physisorption. Physisorption means you can take the hydrogen molecule or atom and adsorb onto the surface of the material, so the hydrogen could be absorbed on the surface. Then the gravimetric capacity and volumetric capacity, or gravimetric is about 2 and volumetric is about 20. That's much higher. The temperature, still we are working with 193 Kelvin and pressure is about 100 bars. So much improvement has come on this subject. Much improvement which has come on this subject. Still, many people have thought that the carbon nanotubes and carbon nanofibers, initially they showed some promising hydrogen capacities. However, the reversibility is an issue. The reversibility of hydrogen storage back and forth in a material is a problem because it's only van der Waals or physical adsorption, right? The second one is adsorbed on interstitial sites in a host metal hydrides. That's a very typical one. You take any material like a lanthanum, nickel, or iron titanium, you can find some kind of voids. Those voids in a crystal lattice or crystal structure, you can pack the hydrogen so that you can get a hydride. The most advantageous or most known hydride is the magnesium iron hydride that shows a very high volumetric capacity, about 150 kilogram per cubic meter, and also the temperature is about 303 Kelvin, and the volumetric capacity and so lanthanum nickel 5 also having the same volumetric capacity. So we will talk about in future virtual academy if we get an opportunity to discuss about these individual compounds. Complex compounds like aluminum based compounds or boron based compounds, they all now very hot and then very rigorously researched. That is, these compounds having both the gravimetric and volumetric capacities are much higher, and they work at lower temperatures, about 373 degrees Celsius or 373 Kelvin, and then probably about room temperature degrees Celsius. So what we have done in our research is adsorb hydrogen physisorption. We also look into some polymeric compounds, polymer nanofibers and nanospheres, and then we have done some rigorous research on complex compounds, that is based on lithium, magnesium, all the lightweight elements. with hydrogen storage properties. So, Sridhar, how much time I have?
20 minutes, sir.
Okay. So, this slide, I'm going to discuss about what is, say, we started from the macro picture. The macro picture means we started from the overall big scenario of energy production, storage, and fuel cells. And then we came down to number of types of storage materials. So now let's get into metal hydrides, because those are the reversible hydrogen materials. What is actually happening in here is, on the top layer, you see the hydrogen is always in form of a molecular form. So hydrogen molecular form is supposed to split into hydrogen atoms, and these hydrogen atoms split by a catalyst which is appeared on the surface. So these hydrogen atoms, which then located into the voids of a crystal lattice, what that called hydrogen stored in a solid compound. So during this process of metal plus hydrogen to give a metal hydride, then that is called exothermic react. I'm sorry, this is a hydrogen molecule. So you're getting into M plus H2 gives MH plus heat out. So you're taking the heat out. But if you're providing the heat into the metal hydride, you can also release the hydrogen and then the M free. So basically, this is a stepwise process of exothermic and endothermic reaction involved, so that you can produce the hydrogen by means of storing back and forth with the metal hydride system. So this is just a big view, but we can go into deep and look into that, what is actually happening in the microstructural sense. The one underneath the hydrogen intercalation in metal hydrides, you see two types of structures available so far in our crystal systems. That is, hydrogen could be localized into tetrahedral sites. That means there is a red atom which is sitting on the tetrahedrally, or hydrogen could be occupied into octahedral sites, that is with the 6 hydrides. So there is a octahedral sites, it is just a cross-sectionalized, so you can see that the hydrogen could be localized into tetrahedral or octahedral sites. And also one other thing we have to remember about temperature. The temperature and then the enthalpy. Enthalpy is the heat of reaction, how much kilojoules per mole of hydrogen needed. So on your left hand side, there is a bar chart which shows that number of different materials work at different temperature regimes. For example, you start with the 0 to let's say 0 to it's less than 100. It's more like a cryogenic temperature. Cryogenic temperature. Then the carbon, like carbon nanotubes, single wall nanotubes, multi-wall nanotubes, their energy or delta H is about 4 to 20 kilojoules per mole hydrogen. And then if we go, so about 10% of LHV. And then the intermetallic hydride, what I said about the lanthanum nickel 5 iron hydride and all these, they do have the hydrogen absorption, desorption about 0 to 100 degrees Celsius. That means a low temperature to room temperature to low temperature. The delta H required for this is about 30 to 55 kilojoules per mole hydrogen. Whereas on the higher temperature, where the complex hydrides work on ionic and covalent hydrides, they have about more than 100 degrees centigrade. It could be 200 to 300 degrees Celsius. The delta H is about 70 to 80 kilojoules per mole hydrogen. So Again, like it's up to the researcher to decide that what temperature he is looking for to make what kind of material. And on the other side, on your right hand side, the plot shows the energy with respect to delta H. So, for example, if you are going from your reactant side, if we're going from the reactant side and getting to the product side, there's a huge barrier, the huge thermodynamic barrier, which causes this many of the hydrogen storage materials not functioning very efficiently because of the thermodynamics. So the delta H is the EA is activation energy, delta H is enthalpy of reaction. So as a hydrogen storage or energy researcher, then he has to consider the thermodynamics of the system and then the kinetics of the system. The kinetics means how fast the hydrogen can be released and stored back. So how fast the hydrogen can be released and stored back, and then what are the temperature regimes in which you want to work and then use it for your fuel cells or internal combustion engines. So the various materials have been devised for storing the hydrogen so far. The elements in terms of alloys and complexes. So people have started working initially with intermetallic compounds like intermetallic such as AB5, AB5, AB, AB2, A2B like that. And also we prefer the solid solutions using vanadium based solutions. But the problem with this or intermetallic compounds, they often have a very low gravimetric capacity, less than 2%. That's no good for a fuel cell or internal combustion engine. So then we went on to other systems like some of the stable and metastable systems like multiphasic compounds, quasi-crystalline, amorphous and nanocrystalline compounds. So these compounds, they do have some interesting properties for storing in the grain boundaries and grains and multiphasic natures. But however, the gravimetric capacity is not yet improved. Therefore, a new sort of complex compounds have been introduced by scientists called Bogdanovic in Germany. That's a sodium aluminum hydride. He throws some titanium into the sodium aluminum hydride. That becomes more like catalyst for the whole industry. Whole academic have started working on those complex materials. So the complex hydrides could be classified as transition metals, non-transition metals, other compounds. Transition metals basically based on your transition group elements like nickel, cobalt, iron and other elements. Non-transition also you have sodium aluminum hydride, lithium aluminum amide, boron hydride, so on and so forth. Again, it takes a whole different another virtual academy to go and deeply dig into what is actually being done and then why are we choosing some new compounds. So I'm just giving this hint that these are number of variety of materials have been devised since 1950s. Because the first metal hydride was synthesized by Dr. J.J.H. Raleigh from Broeka National Lab. And also there was some report from Philips Research Lab in Netherlands. So it's about 40 years or more than 50 years now. The research is looking for some new paradigm to get the Department of Energy storage goals achieved. Number of methods we use often for looking at this making the materials. Synthesis mechanism, we use radio frequency induction melting, spin melting, mechanical alloying, salt gel reverse meiosis, servothermal, hydrolysis, thermochemical, mechanochemical and chemical synthesis and purification. These are various synthesis methods where you can produce hydrides, and we use characterization like X-ray diffraction, neutron, diffraction, transmission electron diffraction, scanning, electron diffraction, energy dispersive X-rays, differential scanning, calorimetry, BET surface area, thermogravimetric analyzer, pressure composition isotherm, Fourier transform, infrared spectroscopy, UV-Vis, Raman and GCMS. Some of the properties which are very pertinent to this project is about kinetics and cycle life, degradation, electrochemical and hydrogen storage, catalytic, structure, microstructure, thermal gravimetric, thermal calorimetric, volumetric and gravimetric properties. Again, all these we need to establish tools to do all kind of research. So, in this schematic, you see the hydrogen molecule comes and sits as such as a molecule binded onto the material. That's called molecular chemisorption. The second case, a molecule dissociates using a catalyst and then produces what you call hydrogen atoms, that is atomic chemisorption. The third case, the molecule as such bind onto the substrate, that's called physisorption. So you have three types of mechanism occurring on this surface. One is molecular chemisorption, that's molecular hydrogen absorb on the surface. Atomic chemisorption, that is the hydrogen atoms absorb or probably interlock into the lattice of the system. And physisorption, physical van der Waals bond attraction onto the surface of the substrate. So this I have discussed already, that how we make the synthesis, characterization, performance testing for hydrogen storage. We also use some new material discovery by means of destabilization mechanism, nanocrystalline, nanomaterial doping, and use some theory like a density functional theory for looking at the viable hydrogen storage materials for fuel cell and internal combustion engine applications. So this is again the big chart of what are the capacity or capability what we have for looking at the different systems. On the left hand side is a ball milling instrument for making into the hydrogen storage materials with a very high revolution per minute, about 800 revolutions, string manifold, glove box for preparing these materials, PCT, pressure composition isotherms for making the hydrogen absorption, desorption, simultaneous differential scanning and thermogravimetric analyzer, DSC, XRD, TEM. XRD is X-ray diffraction, transmission electron microscopy, scanning electron microscopy, AFM atomic force microscopy, and thermal program desorption to look for the gas analysis of the hydrogen which is coming out of the sample. So, couple of patterns we have developed based on devising these materials. One of the pattern which was approved in 2013 of mine is method of generating hydrogen storing hydrate complexes. The second one is hydrogen storing hydrate complexes in terms of nanotechnology. So a couple of materials we were trying to understand. This is the option of weakly bonded polymer nanostructures, increase the surface area on polymer and decrease particle size. Chemisorption of some complex materials like lithium magnesium compounds and using mechanochemical synthesis and particle size reduction. Additives to reduce the enthalpy and enhance the kinetics. So with this, I would like to, I'm not going in detail with my research, but I will take another opportunity with IUCEE to go and explain about the further research. With this, I would like to thank Dr. Krishna Vedula, Professor Dean Emeritus, IUCEE, for providing this platform and opportunity to talk to you folks. Thank you all, Mr. Sridhar for IUCEE, for CEE, for technical assistance. My university, Florida Polytechnic University, which is a very very newly built. If you look at my, this is my university campus. What you see in here on this tomb, this is a building called Innovation, Science and Technology, a technology building. So this campus has we have started this 2 semesters ago. Last year only we started. So this is a very pretty new campus, and then we offer College of Engineering, College of Innovation Technology, Master of Sciences, Master of Engineering, and many other fields. So if you happen to come here, you are welcome to visit us. And if you have any questions, thank you very much for you all for your attention. If you have any question, please let me know. Thank you. Hello, Steven?
Yes, sir. We'll give them 1 or 2 minutes to type their questions.
Okay.
One of the participants asked, can this hydrogen be stored in the labs?
Hydrogen is stored in the labs. Yeah, that's a good question. That's a very good question. Hydrogen as such, you can bring the hydrogen bottle from the vendor for store it in a lab for doing some research. Again, the hydrogen, of course, you have to find a secure way of securing this hydrogen in a canister inside the lab, and make sure that there's no leakage or anything on this. But for the preparing the hydrogen materials, the hydrogen materials will be handled primarily inside the glove box. The glove box means the glove box contains the nitrogen ambient, that's a inert ambient. So you will open the hydrate canister or probably ball mill container, the load or unloading or loading the material for hydrogen absorption. Everything should be done with a very precautiously using a glove box for doing this. So for just a very serious research is going on, and if you want to get this done, yes, if this can be done in a safe way. In a safe way in the sense, you have to follow the procedures. You have to get the safety protocol which has been you have to approve from your environmental health and safety to see everything is correct before doing this. This can be done. People have done in India. They use the hydrogen for storing in a vehicle and all. So it can be done. Only safe way is provided, needed.
One of the participants is asking if he can have access to your slides.
Yeah, this I'll trim some of the things and I'll convert that into PDF file and then send it to IUCEE so
Thank
that
you,
you
sir.
can. Yeah.
Sure, sir. Thank you. What is the best ratio achieved of energy output, energy input using hydrogen?
Can you repeat it?
What is the best ratio achieved of energy output, energy input using hydrogen?
Yeah, the best ratio is so far ideally if the perfect reversible cycle, then I would say that about 3% is reversibly, 3 to 4% is reversibly achieved back and forth for 1,000 or 2,000 cycles. So what that means, I'm more like I'm looking more into the system level or to the level where it can be applied into your automobile. So if you want to get this automobile running for about 70 kilometers, at least 3% is safely achieved so far, 3 to 4%. Japan has achieved, Toyota has come up with 3 to 4%. And then people have started talking about 5 to 6%, but that's a long in the higher range. But we haven't seen any data supportive of that about more than 50 cycles. So I would say for that means 3 to 4% of hydrogen could be reversibly stored and take it back for your applications. Is that answer your question, or is that any? The ratio means, I would say, like if the question, the person asking about ratio, let's say 100% ratio, no, it's not in 100% ratio. So about 30%, 30 to 40%, I would say.
When using graphene-based metal complex, what is the efficiency?
Graphene is has shown much improvement in recent years. Graphene have shown a lot of potential promise for semiconductor industries, electronic industries, and microchip industries, and many things. But the graphene also have shown some papers have shown like you can because graphene is made of a lamellar structure, so where you can pack the hydrogen to the level where you can store it. The I would say at this point, not more than 1% hydrogen capacity reversibility is achieved in graphene. Graphene, still people are trying with the graphene with the polymer nanofibers and polymer matrix, but still the graphene is a good to start research. But so far, people have attained about 1% or 1.5% reversible hydrogen capacity.
H2 is not an inactive gas. What is the use to keep in a bulb?
Can you repeat it?
H2 is not an inactive gas. What is used to keep in a bulb?
In a bulb.
Yes, sir.
H2 is not an inactive gas, but H2 is hydrogen is, as such as I said in the first place, hydrogen is a flammable gas. So even if it gets a small portion of your oxygen visibility, it catch fire. So that's the one thing, that it is not an inactive gas, it is an active gas. I'm not sure that whether the person understand that hydrogen is a very reactive gas, not the inactive gas. So it is a reactive gas. So that is, and then, so if hydrogen bulbs and hydrogen arc spectrum, they use hydrogen as a glow discharge. because they produce they put the electricity on through two leads, and then they produce the arc discharge or a hydrogen arc discharge. So I want to make sure that the hydrogen is not a inactive gas, it is a reactive gas. It does react to the atmosphere like oxygen or any other, like even if you have some residual moisture or a residual hydrocarbon, it could react onto that. So it's a reactive gas.
System level energy input required to get 100 units of energy output.
System energy, what?
System level energy input required to get 100 units of energy output.
Yes, theoretically it is, yes. Theoretically, if you want to get the system energy to the level where you want to get 2015 or 2020 targets, you need to eventually work for 100% to get that output. But the thing is, none of the material on the earth is having the very high capacity or a high gravimetric capacity or a high volumetric capacity or a low temperature and so forth. So since none of the materials so far devised or discovered so far shows that 100% of systematic capacity, so it's a keep on everyone is in a race. Like in Europe and Japan or in India or in US, everyone is trying to see that whether they could reach at least 50. So right now it is say about 60%. If you can solve the energy demand or energy system level efficiency, that's much better. So still people are looking at the various way of improving the capacity of the kinetics, but still we are not there yet.
Those are all the questions, sir. Thank you very much for the informative webinar, sir.
Thank you. Thank you very much. Thank
Thank
you.
you.